sense that the technique I'm going to tell you about first is seriously antiquated, at least in the forensics realm. Though Jeff says that he uses a modified version of this to figure out single letter differences when he wants to figure that out in some cases. But the basic idea is, okay, it's only antiquated in the forensics realm, all right? But if you think back pre-molecular biology, if you wanted to solve a crime, one of the big innovations that came about was the recognition that everybody has unique fingerprints, and that if you compare fingerprints and you find matches between fingerprints left at the scene of a crime and fingerprints on a suspect, that the court will say, like, okay, yeah, that means that their finger was present at the scene of the crime, and if their finger was present, that means they probably were present also. And so we use the presence of a fingerprint as an indication that a person was at the scene of a crime. Now, as you move forward in time, you may not always have fingerprints, but you might have like blood, say, from the victim in the car of the suspect or vice versa. And so one of the things you can do to exclude possible suspects is you blood type the blood and you blood type the suspect. And that lets you figure out very quickly if somebody can be excluded as a possible perpetrator, right? If the suspect has blood type O and the blood left at the scene of the crime is blood type AB, well, you know you're looking for somebody with blood type AB. Now, if you find somebody with blood type AB, does that mean they committed the crime? No. Lots of people have blood type AB. So moving into the realm of what's called DNA fingerprinting, and this, if you watch some of the older CSI shows from like the 90s or early 2000s, this would be the technique that they use. What they do, you probably have seen images like this, where you see these forensic specialists holding them up to the light and scrutinizing them, things like that. Has anybody seen images like this on forensic shows? Well, what these are doing is they're taking advantage of the fact that restriction enzymes only cut at a specific sequence. And so even if you don't know much about the individual or about their DNA, if you take their DNA and you cut it with a certain restriction enzyme, and you compare the pattern that results with DNA extracted from blood left at the scene of a crime, and if you see differences between them, you know that those are two separate DNAs because there were different numbers of times a given restriction enzyme cut. So just to make that a little bit more concrete, if you imagine these are two different individuals' DNA, this is perp1 and perp2, all right? I should say suspect 1 and suspect 2. And these are their DNA. If I take their DNA and I expose it to like BAMH1 or one of those enzymes, if these red areas, these thick areas are restriction sites for that enzyme, it's going to come in and cut right there, cut right here, and cut right at that point. So then if I take that DNA and do what you guys did today, load like perp1's DNA here and perp2's DNA here, we can separate out those fragments of DNA based on size. And so when you run these gels, what you should see is both perp1 and perp2 should have DNA of this size. So they should have a single band that matches. And maybe I'll put that right here. Those are supposed to be at the same point. There we go. All right. Now, perp2, because it has one less restriction site, is going to have also a fairly large fragment. So those are the two bands that come from perp2. The large band that ran to here and the slightly smaller one that ran down to here. Now, because this was cut once in perp1, we reduced it slightly in size, so it might run down to here. And then there's a teeny little fragment that might run all the way down here. So what you can do is you can basically just digest the DNA of all the suspects, digest the DNA from the scene of the crime, and then there's some techniques that let you visualize where the DNA is. You just compare bands. So in this case, if you look, who did it? If this is the blood stain left at the scene of the crime. This guy?
Yeah.
Yeah, pretty easy, right? And it's maybe a little bit more complicated than this. That's the basic idea, is literally you just look for shared bands. And those indicate shared restriction sites, which mean you have the same sequence at that point. All right. So these techniques require large amounts of blood to work with. So that's easy to get from the suspect, but what if there's just a teeny little speck of blood somewhere? Like, you know that you think this person killed somebody, but there's just one little dot of blood left in their car. Not enough to actually do this. What do you do?
The other methods that don't work as well.
Fingerprinting, blood typing?
Could you copy their DNA?
Yes, indeed you can. So you can use this technique. Very good question. Very good point. You can use this technique that's called the polymerase chain reaction. And what this lets you do is copy from a single or a few copies up to billions and billions of copies of DNA. So it's a pretty cool technique that actually, I think Kary Mullis won the Nobel Prize for, I think it was chemistry. I think that was the discipline he won it in. But it's kind of weird to win the Nobel for just a technique, like the PCR. But this guy, Kary Mullis, did. And what's kind of cool about the story of Kary Mullis, let me just skip ahead right here. So he worked for a big biotech company at the time he invented it. And because when you work for a company, they own the patent rights to what you invent while you're there, he invented this technique. And the story that I heard was that he received a bonus for inventing this technique of something like $10,000 or $50,000 or something. But the technique has become so important, so universally used in all laboratories everywhere, that it's made hundreds and hundreds of millions of dollars for the company that he worked for. If you work at an academic institution, you don't have to pay royalties for doing PCR, but if you work at a for-profit, like, you actually have to pay patent royalties for each PCR reaction you do. And I don't know when the patent expires for PCR. I think at for-profit institutions, yeah. I believe that's the case. I mean, it's a patentable technology. It's a patented technology. So they may sell the rights to do it. So in any case, he went on to win the Nobel Prize and get something like $1 million, which is what you get as part of the Nobel Prize, and took this to. He quit science, and now he wrote a book that I have an image of the front cover here. Dancing Naked in the Minefield, and he pretty much spends his time now surfing, playing jazz guitar, and smoking weed. So let that be a lesson, all right? All you have to do is win a Nobel Prize to live out the life of your dreams. So